All right, geometry students, today's lesson is all about algebraic proofs. Algebraic proofs are just another way to solve algebraic equations. We're just adding a little bit more logic than you might be used to. So our learning target today is that we can use various properties of equality to write algebraic proofs. In this lesson, we will be talking specifically about properties of equality and reviewing what those are. You use them a lot in algebra. We are also going to be talking about what a two-column proof even is, and we're going to use the two-column proof to write algebraic proofs. Now, it's really important that we are taking notes on this concept. However, it is up to you whether you use the guided notes or not. It may be more helpful to you to use a physical copy notebook. Let's get started. So let's review the properties of equality. We use these all the time in algebra, and I will give you some specific examples of each one. So starting with the addition property. If A equals B, then A plus C equals B plus C. This means that we are adding something to both sides of the equation and it is still balanced. For instance, let's say we have 3x minus 1 equals 8. Well, we need to eliminate this negative 1 somehow, and to do that we need to add 1 to both sides. Since we are adding 1 to both sides, we can eliminate the negative 1 while still keeping the equation balanced. The subtraction property of equality states that if A equals B, any real number A equals any real number B, then A minus C is equal to B minus C. So similar to the addition property, let's say I've got 2x plus 8 equals 3. And in order to eliminate this positive 8, I need to subtract 8 from both sides. And by subtracting 8 from both sides, I am keeping the equation sides equivalent to each other. Multiplication property says that if A equals B, then A times C equals B times C. For instance, if you have the equation x divided by 9 is equal to 1, you can multiply both sides of the equation by 9 to eliminate the operation of dividing by 9 from x. So this would be reduced, and you're still keeping the equation balanced. Division property of equality, it happens very commonly at the last step of equations. If A equals B, then A divided by C equals B divided by C. So let's say I've got the equation 2x equals 4. My last step would be to divide both sides of the equation by 2 to not only keep it balanced, but isolate our variable. Distributive property, I'm just going to mark right on the chart here. If you have the expression A times, in parentheses, B plus C, then that is equal to A times B plus A times C. And we remember from 7th grade that the way that we distribute is that we take the value on the outside of the parentheses and multiply it by every term on the inside of the parentheses. A times B plus A times C. Substitution property states that if A equals B, then A may be replaced by B in any expression or equation. We do this a lot when we check our answers in algebra. So let's say we find the solution to an equation is x equals 2. And we want to substitute the value of x into the equation to make sure that we solved it correctly. So let's say our equation is 2x minus 8 equals 5. So we're going to substitute 2 in for x. That's a perfect example, very common example for us, of the substitution property of equality. Now the reflexive property, maybe one you haven't heard of before, but it's pretty simple to understand. It says for any real number A equals A. That means a value will always equal itself. So you may see x equals x, or 1 equals 1. Whatever value, it will always equal itself. The symmetric property says that if A equals B, then B equals A. Basically, we're flipping the terms to the opposite sides of the equal sign. So let's say you have the equation or solution 3 equals K at the end of an equation. And we just want K to be on the left side, so we can flip the order. 3 equals K, K equals 3. They equal each other. That's the symmetric property. And lastly, we have the transitive property. And this one's a little bit trickier. This one says that if A equals B and B equals C, then A equals C. Basically, this is saying if two values equal the same value, then those separate values also equal each other. We'll look into more specific examples of that in a second. But those are our properties of equality we will need to know in order to complete algebraic proofs. So let's practice. Looking at the chart on your notes, it says name that property. Write the name of the property that justifies each statement. That's what we're going to be doing a lot today, is justifying our statements. So number 1 says if K equals 3, then 3 equals K. Now, to me, that looks exactly like we flipped around the terms on opposite sides of our equal sign. So this would be the symmetric property. And just to save a little bit of time, I'm going to refrain from writing property after each one. We know this is the symmetric property. For number 2, if 2x equals 14, then x equals 7. So we have to take a look at the if portion of our statement and see how the then portion changed. So I'm seeing that the 2 on the 2x was eliminated, which means we had to have divided both sides of the equation by 2. When we do so, x equals 7. This is an example of the division property of equality. Number 3 says that 10y equals 10y. That means a number or value equals itself. That's the reflexive property. Number 4, if negative 5x minus 1 equals negative 11, then negative 5x equals negative 10. Again, we need to see what changed between the if portion of our statement and the then portion of our statement. I'm seeing that the negative 1 was removed, which means it was added. We added 1 to both sides of the equation. This would be eliminated, and then negative 11 plus 1 does equal negative 10. So this demonstrates the addition property of equality. We added 1 to both sides. And number 5, if 10a equals 2b and 2b equals c, then 10a equals c. So let's take a look. I am seeing some things in common here. I see that 10a equals 2b. I also see that c equals 2b. So that means if we substitute, we see that 10a also equals c. This is the transitive property in a nutshell. This is the transitive property. So what I would like you to do is I would like you to take the time to practice with the remaining problems in the table, and we will be ready to move into algebraic proofs. So let's talk about it. What is a two-column proof? What's this proof we're even talking about? So a proof is just a way to organize a problem logically to come up with one solution. The two-column proof is a common format used to organize a proof. We are given a statement, we're asked to prove something. So, the statements or steps of a proof are listed on the left side. We're going to create a two-column proof. Looks something like this. You've got a statement side on the left where you list all of the steps to solve your problem. The right side of the proof is where your reasons go. Your reasons are what you're using to justify each statement you made in the left column. For every statement, you must have a reason. That's how a proof works. So some specific types of justifications can be used for reasons. Those include our properties, like properties of equality, right? Those include our definitions. So definition of congruence, definition of a line, etc. It goes on forever. We can also use postulates, like the segment addition postulate or the angle addition postulate we've learned about. Those are statements that do not have to be proven to be true. We just accept them as true. And theorems, like the Pythagorean theorem. Theorems are statements that must be proven to be used. So the Pythagorean theorem, you can look up a proof of that or multiple proofs of the Pythagorean theorem and see logically why it works. And then you can use it in proofs. So let's try out a mostly filled in algebraic proof. We are given the statement -9 times 2x minus 3 equals 63. And we are asked to prove that x equals -2. Now, in a two-column proof, we always start with the given. We always start, the first reason and statement are the given statement. That's why the equation was just transplanted right to step 1. Okay? Let's look at the change between step 1 and step 2. So what I'm seeing happening is we distributed the -9 to both terms in the parentheses. -9 times 2x is -18x. -9 times -3 is +27. So the second step showed the distributive property of equality. This was the distributive property. Now, moving on to the third step, we notice that something else happened between 2 and 3. I'm seeing that what happened was this +27 was somehow changed. In our case, logically, we know that we need to subtract 27 from both sides of the equal sign, and then it eliminates. So we're left with -18x is equal to 36. What we just did between step 2 and step 3 to justify our actions was the subtraction property of equality. Subtraction property of equality. And last but not least, to get from step 3 to step 4, our statement is now x equals -2. So what had to have happened was we needed to divide both sides by -18. We just used the division property of equality. And you'll notice that at the very end of the proof, we ended with the prove statement. So again, start with the given statement, end with the prove statement. And really, if you know how to solve algebraic equations, the only part we need to remember is inserting these properties of equality and justifying each statement with a reason. There are additional practice problems where they are partially filled in, where you're only filling in the reasons, and those are problems 1, 2, 4, and 5 in your notes. Well, let's try something more complicated. Let's try one without statements given to us. So we're going to have to solve this one from scratch. So we are given the equation 5y minus 1 divided by 2 equals 7. And we're asked to prove y equals 3. So to start out, I know I need to start with my given. So first step, I'm going to rewrite my given statement. 5y minus 1 divided by 2 equals 7. And the reason? That's given to me. That's given. Now my next step, now I need to take a look. What's the next thing I need to do to solve for y? Well, to me, I need to do something about this division by 2 here. The inverse of dividing by 2 is multiplying by 2. I'm going to multiply both sides of my equation by 2. Now in an actual 2-column proof, it's not going to be this messy. I will clean it up. But for statement 2, I'm going to eliminate here, and I'm left with 5y minus 1 equals 7 times 2 is 14. And so what I just did was use the multiplication property of equality. I multiplied both sides of my equation by 2 and kept the equation balanced. Now my next step, the next thing I need to do to solve this equation, we know we need to add 1 to both sides. And I'm not going to show that step just to keep the proof looking kind of neat. So I add 1 to both sides. This eliminates the negative 1. I'm left with 5y on my left side. And that's equal to 14 plus 1, which is 15. And so my reason is I added 1 to both sides. That is using the addition property of equality. And my last step, to isolate my variable, to get to my prove statement of y equals 3, I'm going to need to divide both sides of my equation by 5. And I get y equals 3. When I divide 5y by 5, I get 1y. When I divide 15 by 5, I get 3. And the property I used to get to my proof statement was the division property of equality. And that is a fully completed algebraic proof. All we have to do is solve the equation in the way we know how, but just make sure that we are giving a rationale or a reason for each step. And I highly recommend that you practice the additional problems. Those are 6, 7, and then 9 through 11. So 9, 10, and 11. Those are available for you to practice with. So that was our lesson. Thank you so much for watching. Please make sure you are trying out at least some of the additional practice problems. We really want to make sure we are using these logic-based steps in geometry. Let's make sure that you are checking your answers with my filled-in notes. Those are located in our class notebook, in the content library, in our Topic 1 Notes tab. Make sure that you're asking for support in the Math Help Desk if needed, and I hope you have a lovely day.